Okay, kids, what I want to do is quickly go over a problem like this. That was the one in the back of LYQ, last year's quiz. Now, in case you don't have it in front of you, I'll read it. I'll read it to you because I'm here for you. Okay, a helium atom has a mass of 6.67 times 10 to the negative 27th kilograms. It is accelerated by a voltage of 4,500 volts. So an electron goes into an electric field, and it speeds up as a result. Now, here's a question. Question, part A, 2 parts. Dos patitos, which is 2 parts in Spanish. All right, A, what will its radius of curvature be if it moves in a plane perpendicular to the uniform field of 0.46 Teslas? So this first part of it is asking, what is the radius of curvature? All right, okay, all right, okay. All right, now, if I want the radius of curvature, we all know the following is really, really true and very, very important. This is, an AP absolutely loves this kind of a question. They love it when you can take 2 different concepts and stick them into a problem like this. So if we have a particle which is moving through a magnetic field, then we know that the magnetic force is going to cause that particle to do what? Come on, we've learned it. Yes, we have. Go in a circle. Yes, right-hand rule. You keep repeating it, and it shows that the particles go in circles. Okay, with me? Yeah, stick with me. So that means that our magnetic force becomes a centripetal force. There is a magnetic force causing something to go in a circle, which becomes centripetal force, so the magnetic force equals a centripetal force. Plug them in. All right, so let's see. Magnetic force for a particle is BQV. Centripetal force, mv squared over r. All right, with me? Now this is velocity and this is velocity. So this velocity will cancel out with one of those. So that's what we're left with. Now this problem, he wants us to figure out the radius. I do believe that's what I said, right? All right, you were paying attention? Paying attention. Okay, yeah, what will the radius of the curvature be? Okay, we're trying to find radius. So we're going to take a radius and set it equal to mv over bq. Burger Queen. Burger Queen. Okay. All right. So now if I have this information, I can go ahead and stick it in here and get this thing done, right? Piece of cake. Piece of cake. Well, let's see. This is a sweet problem. Not only because it utilizes the idea of magnetic force as a centripetal force, pretty sweet so far already, but also we're not going to have something in here. What do you mean? Well, we know the mass of a proton, or this thing, not a proton, this was a helium atom, right? I do believe it was helium atom. Yeah, helium atom, and it tells me the mass of it. 6.6 times 10 to the negative 27. So we know that 6.6 times 10 to the negative 27th kilograms. All right. I need the velocity of this particle as it enters the field. I don't have it. No panicking. We're going to find it. That's why it's so awesome. Great problem. Great problem. Okay, so B and Q, we do have, we were given the strength of the field is 0.46. And we were given, what were we given? What were we given? What were we given? It's a helium atom. Now, if the helium atom is going to have a charge, because if it, actually, I should say actually helium ion. I should have wrote that as helium ion. Here's why. If it's a helium atom, it has no charge. Huh? Yeah, right? I wonder if anybody picked that up. Did you pick that up? You picking up and putting down? Yeah, a helium atom would not have a charge, and it would just laugh at any magnetic field. As it would go through it. It wouldn't be effective. We needed it to be a helium ion. Okay, so a helium ion. I would say helium ion, let's say it's doubly ionized, which means the electrons are gone. It has 2 protons. If it has 2 protons, then we know that the fundamental charge of a proton, we all know, is 1 point positive. It's a proton. If it was an electron, it'd be the exact opposite, but negative. 1.6 times 10 to the negative 19 coulombs is the charge of a proton or an electron, just with the negative. Now we have 2 charged protons here in this helium, because remember, helium is number 2 on the periodic table, number 2. So therefore it has 2 protons, that's what it means, remember? All right, so now we're going to take this and multiply this by 2, and that'll give me 3.2 times 10 to the negative 19th coulombs. That's the charge of this helium ion. And it should have said ion, not atom, because atom, the game's over. The problem's over. It says atom. There's nothing. You can get nothing's going to happen. Ooh, that's an easy problem. What are you talking about? Okay. So let's make this charge down here, 3.2, my charge, my Q, times 10 to the negative 19th. All right, sweet. I just need the velocity. You see, there's the problem here. I wasn't given this is just a sweet problem. Okay, I wasn't given the velocity. Well, how the heck am I supposed to find it? I'm going to get rid of this. Okay, make some room here. Make some room. Okay, velocity. We all remember that energies can be converted from one to another. In other words, a potential energy can convert into kinetic energy, can convert into work. They're all convertible, okay? They're all like a Chevy convertible. Funny. Now, in this case, we have potential becoming kinetic energy. We set those 2 equal to each other because one becomes the other. That's the way life is. Potential becomes kinetic, becomes work, becomes kinetic, becomes work, and blah, 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 blah. Just energy going all over the place. So this is kinetic energy. Okay, now, potential energy, we all remember, going back to electric potential energy unit on electrostatics, we remember that potential energy is equal to Q times V. Yeah, okay, yeah, go ahead, look it up. Go ahead, look on your sheet. Yeah, yeah. This is electric potential energy. It's equal to the charge of the particle times, now that V here, be careful, is not velocity. That's voltage. Ooh, that's where the 4,500 comes in, dear kids, yeah. You see, this is voltage, not velocity. So kinetic energy is 1/2 m v squared. Now that v is velocity, so you gotta be careful of that. It can be a little confusing. So this is voltage, and this one here we know is velocity from the kinetic energy equation. Well, why would I want to know this? Why would I have to know that potential becomes kinetic? Because, well, we got to find the velocity, right? We're so close to figuring out this problem here. We've got to set up with just not knowing the velocity. If I can get that velocity, I'll put that in there. Boom! Problem solved. Okay, so let's get that. Now, do I have this information to solve for velocity? This is such a sweet problem. Let's see. Well, we'll go ahead and get that out of there. Put that as a V again. Okay, so I have the charge of the particle. Yes, that's the 3.2 part. It comes in again. You see, the particle is still there. So well, I'm going to get rid of this. Can you see that? Yeah, you can see that. You got plenty of space. Okay, so that charge of this particle, that's the charged helium ion, not atom, again, it should say ion, times 10 to the negative 19. That's my doubly charged helium, 2 protons, and the voltage was 4,500. That was, that's why they gave me those volts. 4,500 volts is a lot of voltage. I mean, every 4 years in November, I only get 1 volt. I can only vote 1 time for the president. Volt, funny. All right, now, 1/2, the mass was 6.67 times 10 to the negative 27th. And then V squared. All right, still see that? Yeah, okay. So then we're going to solve for V. So I'll get rid of this. Now let's go ahead and solve for V. Oh, man. Okay, lots of calculating here, kids. Lots of calculating. Let's go ahead and take 3.2, second function exponent, negative 19 times 4,500. Enter. Okay. All right, get that. Okay. We're going to multiply it by 2. Multiply by 2, enter. Then divide by 6.67. Try this at home. Don't wait for me. What are you doing? Go sit there in your buttocks. Do it. Do it now. All right, 6.67. Second function exponent. Negative 27. Boom. Enter. Okay. All right, that's what I've got so far. Now the velocity is going to be the square root of that because it's v squared. So we'll take second function, square root, second function, answer, and get, wow, 6,570, 6,000. Let me just check the thing here. I'm checking my answer key from the quiz I posted. Yeah, nailed it. Boom. Okay, I put 6.6 times 10 to the negative, 10 to the fifth. 1, 2, 3, 4, 5. Yeah, 6.6 times 10 to the fifth. Yep, boom, nailed it. All right, so 6.6 times 10 to the fifth. All right, so that's my velocity. Velocity 6.6 times 10 to the fifth meters per second. I want to kind of put a dotted circle. That's not the answer, but that was an important part to get the answer. Now I can put that in here for velocity, 6.6 times 10 to the fifth. And I can go ahead and now I can finally solve for radius. Love this problem. Love it, love it, love it. All right, this is one of those, if you get this right, you do a happy dance. Sprinkler. Okay, let's see. All right. So now we're going to take this and multiply it by 6.67, second function, exponent, negative 27, divide by 0.460, and then divide by 3.2, second function exponent, negative 19, and we get 0.029, or I would say 0.02977, 0.03. Okay, 0.029 or you can put 0.03, it'd be fine. So 0.03 meters. 0.03 meters, we all know, would be about 3 centimeters. All right, about that big. This is a circle in like that going about a circle like that. Okay, we're finally done with that problem, right? No! Actually, that was only part A. Oh my God! All right, well, yeah, let's do part B. So part B says, actually, I don't know what part B says, because I don't remember. We're going to leave this answer here, because we're probably going to need that. Probably going to need that for part B. Part B says, what is the period of revolution? Okay, what is the period of revolution? Well, I think that was about 1776. A period of revolution. 1776. Oh, Okay, tough crowd. Oh, let's get going. This is a long video. I thought it was going to be a quick, well, quick, I mean, relatively speaking. It could have taken me a half hour. I'm doing it really fast, like half that time. That's pretty quick. Okay, so what is the period of revolution? That means the time. Velocity is distance over time. And we know this thing is, this helium atom enters the magnetic field. It's going to go in a circle. Boom, 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 boom. So if it does that, I want to know the time. So time is equal to distance over velocity. Distance around a circle is 2 pi r. 2 pi r, we all know that. 2 pi r divided by v. Ah, crap. What was it? Oh, I remember. 6.6 times 10 to the 5th meters per second was the velocity we calculated. Oh, and the distance, the 2 pi r, that's where the radius comes in. So that's 0.03 here. And you go ahead and solve that, and you'll get the time period it takes to go around. One time. That's what that is, time period around one time. Do that out. You should come out with that right there. That's 2.81 times 10 to the negative 7th seconds. 2.81 times 10 to the negative 7th seconds. That's pretty quick. That's PDQ, people. That is PDQ. Okay, that's like 0.0000028 seconds. That'd be a lot of times per second. I mean, you just really fast. Okay, that's how you solve that problem. I love this problem. I love it, love it, love it. Yeah, yeah, love it. If you know what I mean. Yeah, you know what I mean. Okay, kids, enough for now. See you in a bit.